All right, good morning, ladies. So, today, again, we're going to finish off Doppler Effect. So again, we'll kind of go over that quickly and then finish another example. And then we'll talk about the exam. So what to expect, what the structure is going to be and what you're allowed to have, and et cetera, et cetera. And then we will do a review, kind of a quick review of basically everything that you should have. And then I'll split you off into some group exercises. So we'll have 2 more group exercises today. So, good. So first things first, let me share my screen. All right. So first of all, Doppler effect. Again, what I have scribbled up here. Again, is the apparent shift in frequency due to motion. And again, this can happen one of 2 ways or a combination thereof, where either the observer is moving or the source is moving. So here, this takes into account both of those simultaneously. So for example, if your observer is stationary, then this would just be 0. Or if the source is stationary, then that would be 0. But this says that the apparent frequency is equal to the actual frequency times then the speed of sound plus or minus the speed of the observer divided by the speed of sound minus plus the speed of the source. So again, here in the green, the top ones, those correspond to if they are moving toward. So in this case, that'd be the observer moving toward the source while the source is moving towards the observer. And then the bottom signs are when they're moving away. So that would be observer moving away from the source with the source moving away from the observer. So again, this takes into account both scenarios, so whichever one is actually happening. So let's do an example. So let me bring up the actual slide here. So this says that we have 2 identical loudspeakers. Oops, no, that's not the one I want. Sorry. Sorry. Is it this one? There we go. Sorry about that. So we have a platform attached to a truck which carries 2 speakers, one in the front of the platform and the other in the rear of the platform, where the speakers give off a frequency of 440 hertz. And then it says, if a person who is standing midway between the 2 speakers hears a beat frequency of 10 hertz, what is the speed of the truck? Okay. So this is the scenario I have drawn down here. So here's my truck, has a platform attached to it. So here is my speaker on the left, which has a frequency of 440. The speaker on the right, which also has a frequency of 440. Let's say the truck here is moving to the left, and then there's a person standing here midway between then the 2, which is then going to experience a beat frequency. And the reason that they're going to experience this beat frequency is because, again, here, since the right speaker is now moving toward the observer, this is going to be shifted upwards. So the apparent frequency heard by the observer from the right speaker here will be shifted upward. But since the left speaker is moving away at this point in time from the speaker, this one will be Doppler shifted downward. So instead of him hearing 440 on each side, he's going to hear something higher than 440 on this side and something lower than 440 on this side, which manifests itself as then a 10 hertz beat. So here we're told that the difference between the right frequency and the left frequency, which is the beat frequency, then is 10 hertz. And we want to know from this, how fast is the truck then moving to the left? So this is what we want to know. So let's work on this. So here, again, we know we have a beat frequency, and that's equal to the frequency from the right minus the frequency from the left. Good. So now we're going to use our Doppler effect. So again, write down our Doppler effect so that our apparent frequency is equal to the actual frequency times the speed of sound. What was this? So this was plus minus the observer divided by speed of sound minus plus speed of the source. Okay. Now, in our case, the observer is stationary, so in both cases, we're going to have simply 0 here. So that means for this guy, we can write this as then the actual frequency times simply the speed of sound divided then by the speed of sound, speed of the truck, and then we're going to get a minus frequency times the speed of sound divided then by the speed of sound speed of the truck, since in this case, the speed of the source is equal to the speed of the truck. Okay. Now, again, on this side, what's happening is that the truck is moving toward, or at least the speaker is moving toward the observer, which in this case means it's going to correspond to the negative sign. So once it's moving toward, we have the negative sign. So for this one, since this one is moving toward, this one gets a negative sign. This one then is going to get a positive sign since it's moving away from. Good. Now, they both have f, so we can factor that out. They both have speed of sound, so we can factor that out. So let's write this then as the frequency times the speed of sound times then 1 over v sound minus v of truck minus then 1 over v sound plus v of truck. Okay. Now to combine these, let's then find a common denominator. So let's go ahead and do that. So the common denominator is simply going to be the product of these two. So it's going to be equal to then the frequency times the speed of sound times then speed of sound plus v of the truck minus then speed of sound plus v of the truck, all divided by v of sound minus v of the truck squared with squared. Get Adrian on here. Is everyone okay with this? Hopefully. So here I'm just using that a minus b times a plus b is then simply equal to a squared minus b squared. Okay, so that's what I'm doing down here. And then here I'm then just cross multiplying so that this term goes at the top here and this term goes at the top here. Okay. And this term is now positive because I have a minus with a minus, which makes it positive. So here we notice that speed of the sound is going to cancel because this one is positive, this one is negative. So this just becomes twice the speed of the truck. So finally we're going to get that this is twice the frequency times the speed of sound times then the speed of the truck, all divided by the speed of sound squared minus then the speed of the truck squared. And again, all that's equal to f beat. Now what we want, again, is the speed of the truck. So we want to solve for this guy. But we notice that here we have a squared term, and then here we have a linear term, and then this is just a constant, which means we're going to have to solve a quadratic at the end of the day. So from here, all I'm going to do is I'm going to now cross multiply. So I'm going to multiply this term over to here, and then I'm going to divide this term then down to here. Okay. So finally what I'm going to get then is that speed of sound squared minus speed of the truck squared is then equal to twice the frequency times the speed of sound divided by the beat frequency, all times the speed of the truck. That's okay? So let's rearrange this. So what I want to do is make this guy positive. So I'm going to add it over here, subtract this guy over here. So finally, what we get is, so we get the speed of the truck squared plus twice the frequency times the speed of sound divided by the beat frequency times the speed of the truck minus the speed of sound squared is then all equal to 0. So again, here we just have to simply solve a quadratic. So if I do that, what I finally get is that speed of the truck then is equal to, if I remember right, about 3.9 meters per second, where here I'm using that the speed of sound is 340 meters per second. Okay. Yeah, 3.9 meters per second. Good. Is everyone okay? I said, this stage is solving a quadratic, so let's plug in our numbers and go to town. That would be great. Okay. Okay. So again, this is a nice example with both Doppler and beats. So again, here we're told about the beat frequency, so we can use that beat frequency and using the Doppler shift, again, twice in this case. Oops, what do I do? Previous. There we go. So again, Doppler shift due to the fact that this one is moving toward and this one is moving away. The difference then gives us that beat frequency. I skipped so many pages.
And that beat frequency of 10 hertz, that's what we used and plugged in.
Correct. That's right. So down here where it says that F beat, that's right. That was just equal to 10. That's right. So if I went to my final expression here and I put in all my numbers, that's right. So this would be equivalent to F squared plus twice of 440 times speed of sound, which was 340, divided by 10 times F truck minus the 340 squared is equal to 0. That's right. That's right. Yep. Okay. All right. Everyone's okay? Any questions? Everybody's doing okay? Not too bad, right? Good. All right. So next thing we want to talk about is, so let's talk about the exam. I'm going backwards in my step here. Would you stop doing that? Great. So let's talk about the exam. So basically the exam is going to be split up into two parts. So part one is what I call short answer / quick calculation, and I'll elaborate on that in just a second, what that actually means here. So quick calculation. And then part two is going to be long problems. So let's talk about each one of these. So first off, let's talk about the short answer. So short answer basically means that it'll be some sort of written statement. So basically I'll ask you a question and then you have to answer that question based off of physical, basically based off of physical principles. So for example, let's say I tell you that, going back to 175, let's say I told you that you found yourself on a frozen pond where the coefficient of both static and kinetic friction were equal to 0. How do you get off the pond? So how do you get off? So the answer would be, well, you would take off your shoe or your coat or something and you would throw it. Right? So conservation of momentum tells you that when you throw it, you then have to have a momentum with exactly the same amount of momentum at which you throw it. In that case, you're going to have momentum moving in the backwards direction. Since there's 0 coefficients, you will continue to slide until you reach the side of the pond. That would be the answer. So in this case, the physical principle would be conservation of momentum. So you're just going to use and throw something to use conservation of momentum to carry you all the way to the side. Okay. So that would be short answer. So short answer, again, would be some sort of say written argument based on physical principles. So there should be no calculation for a question like that. A quick calculation is exactly that. So it's something that should only be maybe a couple lines of algebra. So it should be something that's fairly simple to calculate. So this would be some sort of simple calculation. Okay. So again, this should be maybe a few lines of algebra. A few lines of algebra. Again, something that's easy to calculate. So for the exam then, there are going to be 5 of these, but you choose 3. So I'm going to give you choices on those. So there'll be 5 of those. So this will be the first thing that you'll see. And then after that, you'll just, choose whichever 3 that you like, okay? You don't have to do all 5. Now, what I have done in the past is you can do all 5, but I'll give you the points for the best 3. Okay, so if you decide to do all 5 of them, and let's say they're all worth like 15 points. So in that case, let's say you get 12 points on one, 10 points on another, et cetera, I'm going to give you the points from the best 3 of them. Okay, so if you decide to do all 3 of them, or sorry, all 5 of them. So here, but again, I'm only requiring that you do 3, but again, if you do all 5, I'll take points from the highest 3. Okay, so this is the first section. The second section then is long problems. So these are going to be multiple part problems. Multiple part problems. So these will be questions going from like A to D or something like that. Okay, so usually about 3, maybe 4 parts. Now it could be that inside of these questions are also arguments. So again, I might ask you, for example, what's conserved in this problem? And then you'll have to tell me what's conserved. So you'll say, maybe energy is conserved or something like that. Or I'll ask you a question about the frequencies. How does this frequency relate to this frequency? And then you would just have to explain something about those. So this is usually going to be some sort of explain type question. So this could be, again, this could be embedded inside of one of these. The rest of it is just going to be some sort of calculation, similar to the group problems, homework problems, things like that. So, but again, these are multiple part problems. Here, there will be 2 of these. And you'll do both. Okay. So again, part 1, there'll be 5 of them. You'll choose 3. And the second part, there'll be 2 of them. You'll do both of them. Okay. Again, multiple choice questions. And then typically, after all of this, there will be a third section. Actually, another one on here, which will usually be an extra credit question. So there will also be an extra credit question. So when you get the exam and you see there are actually 3 questions here, don't be alarmed. One of them is an extra credit. It will say extra credit on it. Okay, but again, the first 2 will always be the ones that you have to do. So again, there will be an extra credit question on here as well.
I don't know if you can answer this or not, but extra credits, they tend to be based on what is talked about in class, or is it random physics knowledge, or is it
Good question. So I have done both in the past, but in this case, it'll be purely what we've done in class. So what I have done before, when I used to teach at liberal arts schools, I had extra credit questions that were based off of general knowledge of different things. So I would ask biology questions and chemistry questions and music questions and all kinds of different stuff. Because it was a liberal arts school, you're supposed to learn about everything. So I would just ask questions randomly about everything. But since USI is not a liberal arts school, then I haven't done that. So it's an actual question. So it'll be a physics question. Now that's actually a good point that you're bringing up. Basically, everything that's going to be on this exam should be self-contained to everything we've done in the class. So I'm going to try to massively limit the amount of stuff I ask from 175. So things like conservation momentum, that wasn't really a topic that we did, so I won't ask any questions on things like conservation momentum and things like that. So all of the questions, whether the short answer ones or the long problems, will all be, again, contained with what we have done this semester. Is it okay?
For the long problems,
yes.
when you have parts A through E,
yep.
If there's compounding math, we find a term in part A and plug it in part B.
Yes.
If we get part A wrong, does that then?
No, then as long as you do part B correct based off of your wrong answer that you get from part A, then it will be 100% correct. Yes.
Okay.
Yes. Yeah, and as you know, that'll unfortunately happen. So, or if you just didn't even do part A, then, as long as you do all the, say algebra correctly for part B, and then just say, at this stage I would put in what I found from part A, then it would still be absolutely correct. So that's right. So when it comes to grading, that's a good point. So I don't do double jeopardy like that. So if you do part A wrong, but you use it correctly in part B, you will get 100% in part B. I'm more of a process person, so I want to see more of how are you going through the problems as opposed to the correct answer. So one thing I usually try to promote, especially in an in-class setting, since we're online, is a little bit different. But since you have limited time, what I usually suggest is to go through all the problems in just an algebraic form and then put in all the numbers at the end. So basically do every problem algebraically and then go back and basically use your calculator at that stage and then do all your numbers at the end. So if you did that, if you did everything perfectly algebra-wise and you never got a chance to calculate your number, I would take maybe a point off of each question just for not actually having a number. So basically the majority of the points are going to come from the process of which, you know, you're showing me that you know how to actually do the problems. So yeah. I don't like numbers, so it's fine. Okay. Everything's okay? So things you're allowed to have. So let's talk about that. So let's go to the next page. So you are allowed an equation card. So obviously I can't check this, but this should be a standard size index card. You really shouldn't need anything greater than that, but that's fine. Standard size index card, both front and back. So that's first thing. Second thing then is going to be obviously a pen or a pencil. Pen/pencil. Third is a calculator. And then 4 at the very end. Something to take pictures of this. So again, pictures or scan. So again, what you're gonna have is you're gonna upload all these onto Blackboard. So basically, over the weekend, I'll get everything set up. So if you want, over the weekend, you can upload the extra credits, the outside of class extra credits, as well as the group assignments. So that we don't have to worry about uploading those on the day of the exam. You can do them prior. They'll have their own separate links. Otherwise, each problem will have a place that you'll upload. So problem 1, you'll have the short answers will all be uploaded together, and then problem 1 and problem 2, and then the extra credit. So each one you'll just upload separately, just like we do in the lab. So basically, you just click on the link, submit, browse, and then attach it, and then submit it that way. And then I'll grade it right on Blackboard. Okay. So on your equation card, things not to worry about for your equation card. Don't put any constants on there. So your equation card, no constants. Reason for that is I will give you all constants. So basically, the way it's going to work is the first page of the exam will basically be instructions as well as all constants and things like that. So let me give you an idea. Let me show you one of my old exams here. Let's find a random exam. Okay, great. So this is fall of 15. So you can kind of see what it looks like. So this is what the exam will look like. So again, you'll have all your instructions, and then basically on the first page, you'll find some useful equations, conservation, in this case, conversions, constants, everything will be contained right on the first page. Okay. And then after that, second page, this is we all the short answer questions, and then your long problems. So the long problem, second long problem, and then some sort of extra credit at the end. Okay. So the first page, like I said, whatever constants you might need, these will all be contained on here. So don't bother using any room on your equation cards because I'll put all the constants on there for you. Okay. So this will be more important when we get to things like electricity. You'll need to know the mass of an electron, the charge of an electron, the mass of a proton, the electric constant, blah, blah, blah. All that stuff will just be on the first page. Okay. Everything's okay?
I had a quick question.
Sure, Kelly.
So I know that you posted like practice exams as well as like the extra credit, but
Yep.
we're not we're not turning in practice exams, right? For anything?
Correct. So the practice exam is just for you to get some extra practice and see what types of questions I've asked in the past and things like that. Solutions for those, I will post those either today or tomorrow. So that way you'll have the solutions going into the weekend and give you some extra practice. But,
okay.
Yeah. So the only things you'll be uploading are the group assignments. And as of today, we'll have 6 of those. So that's 6 points of extra credit. Plus that extra credit that I posted. I don't remember how many points. Katie, do you remember how many points that was for? No, I don't remember. That's okay. Maybe 10 or 12 points.
Out.
Oh, there you go.
Well, if it's on here. Let's see.
I'm sure I can find it. It's okay. Let's see.
It doesn't say.
Doesn't say? Oh, that was mean of me.
Mine says 10 points.
10 points, yeah.
That's 10 points. Okay, yeah, 10 points. Okay. So basically, if you do the 2 of those, you automatically have 16 points of extra credit going into the exam. So not too bad. Plus an extra credit on the exam itself. So I'm very well known for giving a lot of extra credit points. And one other thing I should say about extra credits is we do drop 1 exam, but I won't drop the extra credit from that exam. So it basically means that even though we have technically 4 exams that count, but we have the 5 exams, so I'll keep the extra credit from all 5 exams and add that on top of all your totals at the end of the day. So it's not unheard of that people get about 20 to 25 points of extra credit on pretty much all my exams. So basically by the end, you can have easily 100 points worth of extra credit being added onto your total at the end of the day. So, yeah. All right. So good. Any other questions on equation cards or anything about the grading schemes or anything like that?
Is the homework still optional?
Sorry, what was that, Tara?
Is the homework still optional?
The homework is still optional, yeah. So I'll see how everybody does on this upcoming exam and probably the next exam. If everybody pretty much tanks the 2 exams, then I'll probably not make it optional at that stage. But right now I have no reason to believe that there should be tanking on the exam. So for now, everything is still optional. That's right. And there was another question as well.
So do we just have the whole class time? That's all?
Overall, I'm going to give you, what I say, an hour and a half or an hour 45 minutes, basically to do the entire exam and to make sure you get all the pictures and to make sure everything is uploaded. So basically, what will happen is on Monday at about 8:55-ish, something like that, the exam will be up. So that's when it'll post. And then the links for where you have to submit everything will automatically shut down at about, so I think I said hour 45 before. So at 10:45, then those links will disappear. So basically you'll have until 10:45 to make sure you get everything uploaded. Of course, if you have internet issues, just let me know. I'm not going to penalize you for internet issues, things like that. But yeah, so what I would say is pretty much use the entire class time, that hour, 15 minutes to do the exam, and then give yourself that extra half hour to do all of the pictures and the scanning and the uploading and all that stuff. So yeah. So just think to yourself that, as Molly said, you have the class time to do the exam, and then the rest of the time is there for, internet issues and for scanning and uploading and all that good stuff. So try not to wait till the last second to upload everything. So that's when your internet usually goes out. So everybody's okay? Any other questions anybody has on that?
I have a question. I know it's probably different because this setup, obviously with Corona and all that, is different. But on tests, typically, which tests do people score lowest and highest? You know what I mean? Like, is there like a test that's better?
So out of the 5 exams, so let's see here. Typically, the 2nd and the 4th exams are the worst.
Okay.
Second exam is because that's when we shift now from things that you can visualize to now electricity, where now we're talking about fundamental particles and fields and things that you're just not used to ever thinking about. So the exams usually go down because it's especially in the summertime because it's a hard transition to make. So that's the second exam. But then third exam, things usually go up because by then we're doing things like circuits, which I hate to say it is basically mindless algebra. So students usually like circuits because it's, you know, you're just doing a bunch of algebra, so it's a lot easier. So in that case, score goes up. And then by the time we get to the fourth exam, that's when we're into magnetism. And then again, it usually kind of drops a little bit because we're back in the fields and back into things changing and all kinds of different stuff. So, but then having said that, the fifth exam is usually typically just optics, and students do very well in optics. So usually the best exams are the third and the fifth exam. The worst are usually the second and the fourth. And then the first exam is kind of a somewhere in between. And it's not because the material is hard, it's because you don't really know how I'm going to ask questions yet. So there's that kind of, you know, feeling out period for you to how I'm asking those questions. So it's the same thing in 175. So typically the first exam is a little lower than it should be just because you're not, you know, quite used to how I'm asking questions and things like that. So, but I mean, the first exam is usually pretty good. Like I said, second one, it usually drops a little bit. Third one goes up. Fourth one, it drops a little bit. And then fifth one, it definitely goes back up. So okay. That's kind of historically the way I've seen it happen. So of course, there's always anomalies. So you never know exactly how it's going to go. But everybody's okay? Not too bad. All right. So let's do kind of a quick review. So my reviews are usually just kind of what did we talk about? Here are the equations that you need. And then sometimes I tell you, you know, what to look for in particular problems and things like that. But I've made an exam, but I don't know if I'm happy with it yet. So I might not do that part, but we'll see. So let's talk about chapter 11 first. So chapter 11, we start off with harmonic oscillation. So let's talk about harmonic oscillation. So we have the position of the harmonic oscillator as a function of time is equal to the amplitude times cosine of omega t plus the phase factor. We have that the acceleration is equal to the angular frequency squared times the position, which means that the maximum acceleration is equal to the angular frequency squared times the amplitude. The max velocity is equal to the angular frequency times the amplitude. What else do we have? We had that the total energy is equal to the kinetic energy plus the potential energy, which is equal to 1/2 mv squared plus the potential energy. And then this is 1/2 mv maximum squared. So this is all just the general things over here. Okay, is there anything here I'm missing? I don't think so. Oh, yeah, velocity. So velocity as a function of time is equal to negative of the angular frequency times the amplitude times sine of omega t plus the phase factor. And then the acceleration as a function of time is equal to negative angular frequency squared times the amplitude times cosine, not squared, just cosine. There we go. Omega t plus phi. So again, these are all of the general things. This is true for any type of harmonic oscillator. So these are all general. The specifics, or again, the different angular frequencies. So we have seen 3 angular frequencies. So the first one was the square root of the spring constant divided by the mass. This was for a spring mass system. The second one was the square root of the acceleration due to gravity divided by the length. This was for a simple pendulum. And then finally, the last one was the square root of the mass times g times d divided by the moment of inertia. This was for a physical pendulum.
Can you give a brief description on the physical pendulum again? That one confuses me, just like what they are.
Sure. So a physical pendulum is some sort of rigid body. So in this case, this would be like this pen, or it would be like the water bottle, or it'd be like a rod. So it is some sort of extended body, a rigid body, which does not deform under rotations. So, for example, the one that we did in class was the disc that was pivoted, and then it went under harmonic oscillation. The one that we said was the bar sign. Other things could be, like I said, this water bottle. If I hold it here and I displace it, this thing's going to go under simple harmonic oscillation. So basically, it's anything that is not a string attached to a mass. I guess is the easiest way to kind of say it. So again, remember the simple pendulum is a string attached to a mass. So this has mass M with a length of L. And then again, a physical pendulum would be something like this, where this would be the center of mass. This would be, say, the pivot point. And then again, D is the distance, there we go, from the pivot point to the center of mass. The only other specific thing here is if I'm dealing with a spring mass system, then the potential energy is equal to 1/2 kx squared. In that case, we can write the total energy as being 1/2 k times the amplitude squared. Other than that, again, all of the stuff up here is general for any, again, type of harmonic oscillator. All this stuff down here is specific to a particular type of harmonic oscillator. Okay. So that was all of the harmonic oscillation part. And then the next part of chapter 11, we spent talking about waves. So let's talk about waves. So first things first, we have the displacement as a function of time and position was equal to A times cosine of omega t minus plus k times x plus phi, where again, omega here is the same below, so this is the angular frequency. K here was the wave number, not the spring constant. Phi again is our phase factor. And remember, phase factor is what it's doing at time is equal to 0. And then the minus sign up here means that it's moving to the right. And then the positive sign means it's moving to the left. Okay. So from here, these actually goes in harmonic oscillation as well, but I'll write it down here. We have 2 pi times the frequency is equal to the angular frequency. We have that the period is equal to 2 pi divided by the angular frequency. So this part is actually also true for over here as well. And then we have the wave number is related to the wavelength by 2 pi divided by the wavelength. That's okay. And then we have the speed of the wave is then equal to, in general, this is going to be the wavelength times the frequency, which is also equal to the angular frequency divided by the wave number. And then if we have on a string, then the speed on a string is equal to the square root of the tension divided by the linear mass density, where linear mass density is the mass per unit length. Okay. Let's see, what else did we see? So we also saw standing waves. So let's talk about standing waves. And this was on a string. So for on a string, what we saw was that the wavelength was equal to twice the length divided by the harmonic. So this is equal to 1, 2, 3, and etc. And then the frequency is equal to the harmonic times the velocity divided by twice the length. Trying to think. Is that everything that we saw in that chapter? I think so. Go back real quick. And most everything else we talked about was more concepts, right? Yeah. Just double check. Yep, that's it. Okay. So that's the end of chapter 11. So chapter 11 is all of these things. And again, some of these are for harmonic oscillation as well, but these are everything from chapter 11. So let's talk about chapter 12. So let's do, I don't know, red. That looks good. So chapter 12. So chapter 12, we now applied all that to sound waves. So for sound waves, we then saw things like what? Path length difference. So for path length difference, we said then that the difference in the length, which is equal to d1 minus d2 absolute values, whichever one is bigger, is then equal to either m times lambda or m plus a half times lambda, where this is for constructive and this is for destructive. So this is path length difference. The velocity of the speed of sound in air is temperature dependent, and it's 331 times the square root of 273 plus the temperature in degrees Celsius divided by 273. And then what else? So then we also saw, again, standing waves. So here we had two open. So for two open endpoints, again, we have that the wavelength is equal to twice the length divided by the harmonic, and the frequency is equal to the harmonic times the velocity divided by twice the length, or again, n here is equal to 1, 2, 3, and etc. For one open and one closed, so here we saw the wavelength was equal to 4 times the length divided by the harmonic, and then the frequency is equal to the harmonic times the velocity divided by 4 times the length, where here n now is only odd integers instead of integers. Good. And then after that, we saw what? Beats. Right? Again, we know beats. So a beat. So beat is simply equal to the difference between the frequencies. So it's going to be F1 minus F2, which we call F beat. Okay, so that's our beat frequency. Then we saw the Doppler. So Doppler effect. So Doppler effect again says that the apparent frequency is equal to the actual frequency times the speed of sound plus minus the speed of the observer divided by the speed of sound minus plus speed of the source. Where again the top signs here are what it's moving toward, and then the bottom signs are when it's moving away. Just make sure I didn't miss anything. Oh, intensity, that's what we missed. So intensity. So intensity I is then equal to the power divided by 4 times pi r squared. So this is for an isotropic source. And finally, decibels. So beta decibels is equal to 10 decibels times the log of I divided by I0, where I0 here is the threshold of hearing. Now again, don't worry about writing down I0, that'll be one of the constants on the first page. And I think that's it. Waves, here we got those Doppler. Okay, yeah, I think that's it. So go on. So yeah, so basically these are all the things that should show up on your equation cards. So these are all the necessary formulas that you will need basically to go on those. As I typically I point out what to expect on there, but again, I've written an exam, but I don't know if I'm exactly happy with it, so I might change it. So I don't want to tell you something and then change it, not that be true later. So, but yeah, so probably not everything we did will be represented on the exam. So basically, if it's not represented in the long problems, then it would be probably something in the short problems. But things that definitely look for on there, there'll definitely be Doppler effect. There'll definitely be something with beat frequencies. Definitely harmonic oscillations. So, yeah. Basically a lot of different things with harmonic oscillations, things like that. So,
will the point values be comparable to the practice exam as far as the distribution?
Typically, yeah. So the whole test itself should be about, worth 100 points. So yeah, so each section will say how many points it's worth. So yeah, so that's typically gonna be somewhere between 5 and say 10 points per A or B and C and things like that. So. All right. Any other questions on the exam? Not too bad. All right. So good. So that brings us to the last thing, which are 2 group assignments. So let's talk about each one of these. These are both involving things like Doppler effects. So the first one says that the Doppler effect using ultrasonic waves of a frequency of 2.25 gigahertz is used to monitor the heartbeat of a fetus. So a maximum beat frequency of 260 hertz is observed. So assuming that the speed of sound in tissue, so this is how fast the ultrasound is moving, is 1,540 meters per second, determine the maximum velocity of the surface of the beating heart. Okay, we'll talk about that in just a second. So this has to do with both beat frequency and Doppler shift. We'll talk about how many Doppler shifts there actually are here. And then the second part says, okay, so now that we know the velocity of a heart here, which this is going to be the maximum velocity of the heart, then if it has an amplitude of about 0.2 centimeters, so if the wall is moving about 0.2 centimeters, what is the angular frequency of the wall of the heart? Okay, so this is just purely harmonic oscillation. Okay, so this is the first one. The second one is then this one. So this says we have a microphone attached to a spring that is suspended from the ceiling. See the figure below. Here we go. Directly below on the floor is a stationary 440 hertz source of sound. So that's the speaker down here. The microphone then vibrates up and down. So this thing is going under harmonic oscillation as it's moving up and down, and it has a period of 2 seconds. So then it says the difference between the maximum and minimum sound frequencies, i.e. the Doppler shift, detected by the microphone is 2.1 hertz. So this is our beat frequency. Okay, so this is telling you the beat frequency. So this also has to do with Doppler and beat. So it wants us to take that the speed of sound in air is 343 meters per second. So it wants to know what is the maximum speed of the microphone. So when it's at the equilibrium, either moving up or moving down. What is the amplitude of oscillation? What is the speed of the microphone when it is 0.65 times the amplitude away from equilibrium? So this is what it wants us to find out. So let's talk about the first one first. So let's talk about the fetus one. So this one is a little bit complicated in that you have to understand that there are actually 2 Doppler shifts in this case. And let's talk about why there are 2 Doppler shifts. So there's actually 2 Doppler shifts because, so let's say here's my ultrasound, right? So here's the ultrasound, and it's sending in a wave. So this wave has an original frequency of F. The heart then, so let me just draw this as like a harmonic oscillator attached to a spring. So this thing is moving back and forth. So let's say in this case, it's moving this way. So this is the velocity of the heart when it's at equilibrium, right? So this is at our equilibrium position. So it has the maximum velocity. So what's happening in this case then is the heart is now going to be the observer. So with this original frequency coming in, the heart acts as the observer. So in this case, the observer, i.e. the heart, is going to see a Doppler shift due to the fact that this is the observer. So this corresponds to a Doppler shift by a moving observer. Now, the way ultrasound works, though, is that the original wave comes in, hits the target, and then gets reflected backwards to then the ultrasound machine. And then what it does is, let's call that F double prime. What it does then is it calculates a beat frequency, delta F, which is then equal to that shifted wave minus the original wave, which is sent in. But the reason I'm writing this as F double prime and not F prime is because the reflected wave now suffers a secondary Doppler effect due to the fact that now the heart has become the source. So for the original incoming wave, the heart is acting as the observer. It's a moving observer due to the fact that it's moving. But what that does is it shifts the wavelength to now some F prime. But then that F prime becomes shifted again because now the source is now the heart, because the heart is what's reflecting then that wave, right? So basically the heart now is moving, reflecting the wave, and now it's acting as a source, which is now a moving source. Blue. So now this is a moving source. Reflecting the shifted wave of F prime, okay? So basically the heart is doing two Doppler shifts. It has an initial Doppler shift due to the fact that the wave is coming in and the heart is moving. So what it's going to do then is it's going to reflect that shifted Doppler wavelength back then to the ultrasound, which gives it a secondary then Doppler effect because it is now a moving source. Okay? So basically inside of here, there are actually two Doppler shifts. So there are actually two Doppler shifts. Which means when I write out F double prime is actually going to be F prime times then the speed of sound divided by the speed of sound with speed source. But F prime itself is actually going to be with speed of sound with speed observer divided by speed of sound. But we have to understand that this V of the observer is equal to the V of source, which is simply equal to the V of the heart. Okay. Now, I left the signs out here because now you have to decide what direction is the heart moving. So as I have drawn it here, I have the heart moving toward, but it could be moving away because the velocity is still the same, it's just moving in the opposite direction. So as long as you choose the right one here, I should say right one, but as long as you choose a direction, as long as you're consistent, it doesn't quite matter, okay? But anyways, oops, sorry, times the original frequency. Can't forget about that original frequency. So basically now you have to use this, plug this then into here, and then I'll use this whole thing to then plug into here, okay? So basically, again, there are two Doppler shifts. The Doppler shift comes from, again, the first one, due to the fact that the heart is the observer. But then the second Doppler shift comes from the fact that the heart now is the source. Okay. So these are my two Doppler effects. So this is the first one. So this is group assignment 1. Or 5, whichever way you want to count the order. So the second one, let's go back to this one. So again, here there's a Doppler effect. So what's happening is, again, when the microphone is moving toward the speaker, it's Doppler shifted up. But then when the microphone is moving away from the microphone, it's Doppler shifted down. And what this is saying then is that the difference between the Doppler shift up and the Doppler shift down is simply equal to this beat frequency of 2.1 hertz. Okay? So let's talk about the second one. So this is then going to be group 6. I don't have that much time. So basically here, this is my microphone. In this case, when it's moving downward, this is then shifted upward. So I'm going to get an F up. And then when it's moving away, I'm going to get an F down. And then the beat frequency is going to be equal to the difference between F up with F down. Okay. So this is going to be very similar to what we did with the moving platform, right? So that problem there. So this will look something very similar to this. So in this case, what you're looking for is the speed of the microphone here. Once you know the speed of the microphone, that is going to be the maximum velocity since it's at equilibrium. This is what gives us the maximum shift. So this is when it's at equilibrium. So x is equal to 0. Once you know V max, then you can say, well, this is omega squared times then the amplitude to then find the amplitude. Okay? And you can get the omega from the period, right? So we get omega by saying that omega is equal to what? 2 pi divided by the period. Okay, so this is where omega is going to come from in this case. It's going to give us V max. And then the last part is simply using conservation of energy. So now that we know what the amplitude is, we know what the maximum velocity is, we know the angular frequency, we can then use conservation of energy then to determine the velocity at that point. Okay. So a little bit trickier problems today, but we can all handle it. Okay. Numbers okay? So stop sharing. All right, so there's only about 15 minutes left. So again, I'll split you guys up into factions here so that way you can kind of start talking about these questions. So in the remaining amount of time, and then tomorrow, as I said, because we have that extra day, so we'll start electricity tomorrow, something I usually don't like to do, but that's fine. We'll start it tomorrow. Exam will be Monday, and then we'll keep working on electricity and things on Tuesday. Okay. So let's see some breakout rooms. Okay, so we'll do 3 rooms again. And here we go. Disappear.
Max speed of assuming that the speed of the sound in tissue, would we put that as the V of sound then?
Yes, that would be speed of sound. Yeah. So in this case, your V sound is the 1,540. Is that what it was?
Yeah.
Mhm.
Okay, so
That's right. And then your original frequency is the 2.26 times 10 to the 6th hertz. So that's half. Good. Yeah. So that's it. So at this stage, you just need to decide, is the heart moving toward or away from the ultrasound?
You can just keep it what you had it towards. I mean, I am, I guess.
I'll be right back. Oh, I missed it. Okay, that's fine. So yeah, so all those pieces are basically already set up. You'll just have to put everything together. So everything will be okay.
0.25 times 10 to the 6. That multiplied by the velocity minus 1540 over velocity plus 1540.
How are we doing so far, ladies?
Working on setting it up.
Yeah.
Still working on? Gotcha.
Yeah.
So have you decided, is the heart moving toward or away from the ultrasound? So you're going to do toward or away. And again, that's just to make sure you get all the right, or you are consistent with the signs, so you know which one is positive and which one is negative. So which one do you want to do? Again, doesn't matter.
Okay.
But
I guess we can just do toward.
there you go.
Okay.
Here we go. Okay. So good. So that means when it's moving toward, that means when the heart is the observer, it's going to be positive, and then when the heart is the source, it's going to be negative. So good. So now what we got to do is put all the pieces together. Label me good. Okay. All right. I'll be back. All right. How are we doing, ladies?
I think we're doing okay. Just
okay?
getting the plus and minus signs sorted out.
Good. So which way did you decide? Is the heart moving toward or away from the ultrasound?
We decided on the plus sign, which I think is toward.
So the plus sign for the observer or the plus sign for the source?
For the observer.
Good. So that would be toward. Yes.
Yeah. I was telling them it's a little bit mind-bending because to me, since the heart is the observer in the first part and the source in the second part, it's a little bit like swapping the entire coordinate system halfway through a problem.
Basically. That's right.
It's like keeping track. It's like at first it's the observer and then it's the source. So now we have to switch everything around.
Exactly. Exactly. And it's the same thing if you were doing something like, for example, if you were in a submarine moving towards something, right? So let's say you're moving towards a big rock. In that case, it's the same scenario. So you're sending it out. In that case, then the rock is now, well, it's a little bit backwards, but it's the same kind of idea. So again, there's still two Doppler shifts. So in that case, it would be the submarine is first a moving source, and then it becomes a moving observer. So, yeah. So, but yeah. Yeah, it's a little bit tricky at first, but once you kind of get used to it, it's okay. So. Good. All right. Sounds like you're on a good track. Okay, I'll be back.
For that?
The V observer would be the velocity of the heart, which we don't know, right?
Oh.
Correct.
I thought it was the 260 because it says
260 is the frequency. We're trying to find the velocity of the heart, which I thought he said that for the first round, like the first F's set or whatever, that the velocity or the heart was the observer in that case.
Yeah, it is. Which makes it a little difficult because then that's two unknowns that we have to try and find in order to define that.
Sounds like some algebra right now. Blech.
Well, it's not two unknowns, it's just an unknown that shows up in two places.
Oh no.
Because the heart is the observer and it is the source, but it's still the same velocity.
Okay.
So it's still one unknown, it just shows up in two different places.
Okay.
You doing okay, Emma? You look a little perplexed.
Yeah, I'm just like I'm unsure how to solve for the F prime.
Okay, so well, we actually scribbled it down. So let's go back to what I scribbled down, and hopefully we can make some sense out of that. So how we decided if it's moving away or toward. So is the heart moving toward or away from the observer, or from the ultrasound?
Towards.
Toward. Okay. So good. So let's go with what I have here, so you can kind of see what's going on. So good. So let's write all this stuff down. So let me go to a new page. Good. So in this case, we then have F prime is going to be F times V sound plus V heart, because it's moving toward, divided by V sound. And then we have F double prime is going to be equal to F prime times V sound divided by V sound minus V heart, because it's moving toward. So now all we want to do is take this VF and put it into here. Or sorry, this F prime and put it into here. So this says then F double prime is then going to be F times V sound plus V heart divided by V sound times V sound divided by V sound minus V heart, right? Is okay with that? So this whole term here just comes from the F prime, and then this is what's left over from here. Now notice though that this V sound cancels with this V sound, so it's going to be the same thing then as F times then V sound, yes my son, divided by V heart, divided by V sound minus V heart.
The internet connection is off on TV, but it's on your computer,
Yes.
and on Mommy's computer.
So is that working on the TV?
Yeah.
Did you sign in?
Well, I didn't sign in because the controller is not working.
The controller's not working.
Yeah.
Is it out of battery?
I think so.
We'll go ask Mommy and take a look at it. I'll be down in a couple minutes.
Okay.
All right, we had a tragedy. Okay. Everybody okay? So good. So now what we know is that F beat is then going to be equal to that F double prime minus F, right? So let's put everything in. So that's the same thing as F times V sound plus V heart divided by V sound minus V heart, all minus F. Everything's okay? Now, I'll let you finish it from here. All I got to do now is find V heart. Everything's all set up. Everything's okay? Good. Okay. So, make sure everybody's got that copy down before I run away. Good. Okay. All right. How are we doing, ladies?
I think we have it.
Good. Good.
So I just have like f prime is equal to the frequency, which is 2.25 times 10 to the 6 times 1540 minus VH over 1540 plus VH.
That's f double prime, you're saying.
What?
So that would be f double prime.
Okay, so it wouldn't be f prime, it's f double prime.
Yeah, that's f double prime. So f prime was something that happened before that. But yeah. Yeah, so f double prime would be f, which is the 2.25 times 10 to the 6th, right, times the 1540, and you said minus?
Yes.
Okay, so it's moving away?
Yes.
Good, okay.
Yeah.
Yeah, and then divided by the 1540 plus v hearts, because it's also moving away. Yeah, so that's fine. So that's f double prime. So then your beat frequency then is going to be f minus that quantity. So that'll be your beat frequency. And your beat frequency is that 260. Good. So your 260 then is going to be the equal to 2.26 or 2.25 times 10 to the 6th minus that quantity, and now use that to plug the hertz.
Did you like that?
All right, good job.
Okay.
Okay, so the rest now is just solving some algebra to get v hearts. Okay, good. There you go. All right, I'll be back. All right, how are you doing?
2.25.
Okay, so basically,
Yes.
I I think me and Katie are confused.
Okay.
Okay, so what we did is we went ahead and plugged everything in to the double prime, and
Yep.
we both got something that would completely cancel everything.
Oh, okay. So basically, that shouldn't happen. So you should have opposite signs on top and bottom, right?
Oh,
So
okay.
because what's happening is, again, if it's moving toward, right? So when it's the observer, it should be a plus sign. But then remember, when the source is moving toward, it's a negative sign.
Okay.
Does that make sense?
Well, because the way I had it written down in my notes was that the top signs were toward, and the top sign on the numerator was a plus, and the top sign on the denominator was a minus. So
Correct.
when you flip it, I had them the same.
So we're saying that in the second part of the problem, when the heart becomes the source, it's moving toward the ultrasound?
Yes, because the ultrasound is now the observer. That's
So
okay.
we're always toward, never
In this case,
away.
you're always toward. Correct.
Okay.
Oh, we had it going.
My mistake in defining the coordinate system then.
Yeah, I think we were speaking, instead of speaking for the heart, we were speaking for the frequency from the ultrasound.
Oh, okay.
So we were saying the frequency was going toward the heart and then away from the heart, instead of saying the heart was going toward.
Right. That's right. So we're not thinking about the frequency. We're thinking about what the heart itself is doing. So that's right. So the heart is what's the source and the observer, but in both cases, the heart is moving toward something. That's
Okay.
right. That's right.
Okay.
Yeah. So that's why in the denominator, it should be a negative sign, because it's moving toward the observer, which is the ultrasound in this case. That's right.
Okay, so this is in like the relationship between the source and the observer. So you have
Correct.
to
That's
both
right.
of them.
That's right. Because we're not thinking about the wave itself, because the wave is going to move in all different directions. So we're only thinking about what the objects themselves are doing. That's right.
In reference to the observer.
Exactly.
Okay, and then do we know? Because now I don't know. So we have, a beat frequency of 260.
Yeah, it was given 260 hertz in the
That's
problem.
right.
Where does that go?
Good. So now you're going to have that F beat is equal to then F double prime minus F, right? Because the beat frequency is then the difference between F double prime and the original frequency F.
And the original frequency was just the 2.25 that came out of the
Correct.
original.
That's right. Yeah. 2.25 times 10 to the 6th. That's right.
Alrighty. Well, this wasn't hard at all.
Once we got the coordinate system figured out, you're like, it's usually easier for students when they can visualize it. I'm like, maybe not. It's like, I'm still not visualizing it,
No,
correct?
I'm just a little concerned because I don't feel like I ever would have got there.
That's why we're doing this as a group problem and not an exam question. But
Well, I'm very glad.
I feel like I'd be like over here like, okay, I need to stop and draw a picture. Part A. Part B.
I mean, not to concern you, but this was a exam question at one point in time. So, but I've changed that since. So.
Well, at least we're getting a chance to practice it now.
Exactly. Well, that's one of the points of the group problems that kind of show you what you don't understand, that help you understand it before we get there.
Right. Because this just taught me, like, I understand the math from that point on. It's just like, be very careful, make sure you know what's going on before you start. Because once you define the coordinate system, if you get that wrong, all the math's going to be wrong.
That's right.
And you get 3 or 4 lines down and you're like, something's wrong because it all cancels.
Exactly.
We decided that we decided it was a biological issue at that point.
Yeah, we're like, I'm so sorry, your baby has no heartbeat.
Yeah, your baby would be dead at that stage, unfortunately. So, yeah.
Okay.
All right.
So, 4.
So we are technically out of time, so when you guys are ready, you can take off, and then I'll see you guys tomorrow.
All right.
All
Thank
right.
you.
You're welcome. Let me check on the other groups, and then we'll go from there.
It's like I got it down to where it's like the speed of sound times like that frequency, like the max, the beat frequency, divided by like 2 times
The
0.25 whatever, and then I think you then take that like on like it's on the bottom part and minus that by the 260. But
How we doing, ladies?
I'm not really exactly sure how to begin the second problem. I'm still on A.
For the same one?
No, for the second problem.
Oh, for the second one, okay. Actually, it's identical to what we did with the moving platform. So basically what's going to happen is you're going to say when it's Doppler shifted up, in that case, then you have the object is moving toward. So let's scribble everything down here. Be a little bit easier if I do that. Where are you? Here we go. So let me share my screen real quick. So good. So basically, when it's moving toward, what happens then is that the microphone becomes the observer. So in this case, we're going to have that F beat is then going to be equal to the original frequency times then the speed of sound plus the speed of the microphone, right, which is going to be the maximum velocity, divided by the speed of sound, minus then the frequency times the speed of sound minus then V max, since it's moving away, divided by speed of sound. Okay? So this is going to be the same thing then as what? F divided by the speed of sound times then the speed of sound plus V max. I know how to write. Minus V sound plus V max. Right? Because I have to distribute that negative sign in here, which makes that guy a positive. So again, the speed of sounds are going to cancel. So this is going to be simply twice the frequency times V max, all divided by speed of sound. So here, all you're looking for then is V max. You know what the speed of sound is, you know what the frequency is, you know what the beat frequency is. Sorry, I drew a line from there. And then the 2, so now you can just solve for Vmax. So this says then that the maximum velocity it's going to have is then going to be equal to what? Speed of sound times the beat frequency divided by twice the frequency. Okay. That's okay. So that's 343 times, what was the beat again? 2.1?
Yeah.
Divided by 2 times 440. So this is the maximum velocity. So it's very similar to what we did with the truck one, except here what's happening is that the observer is moving, not the source. So what we did with the truck one is we had the down here because the source was moving, but what's happening in this case is now the observer is moving, not the source.
Okay.
Okay. And then for part B, what you know is that this is also equal to 2 pi divided by the period times the amplitude. So once you find this number, then you can find the amplitude because you know the period, you know 2 pi. So now you can just use this to solve for the amplitude. So this would be for part B.
Okay.
All right. And then part C is just conservation of energy. Are we doing okay?
Yep.
Good. All right. So technically we're out of time. So yeah, so I'll just see everybody tomorrow.
All right.
All right. Make sure everybody else is here.
On Google it, do something like that.
All right, how we doing, ladies?
Good. We think that we figured out the first question pretty well. Whenever we got the answer, the rounding's a little different than with yours. I think we got
That's
like
fine.
0.88 instead of 0.82.
Yeah, that's fine. We're always going to have rounding differences, so that's fine. Just depends when you're using a calculator where you truncate numbers and things like that. So yeah.
Okay.
So rounding issues aren't a big deal.
Okay. And then since we're kind of done with that one, we're not sure if we should even start the second one or just keep.
Well, I mean, we're out of time now, but I mean, you can all talk to each other at some point and work on the next one at some point. Or you can do it by yourself and then compare with each other, however it is that you want to do it. But yeah.
Okay.
Yeah. So I'll leave that up to all of you. All right. So otherwise, I'll see everybody tomorrow. Have a good night, and we'll see everybody tomorrow.
Thank you.
Thank you. Bye.
Bye, guys.